Hey calculus class, today we're going to learn topic 50, Eulers Method, and this is a BC concept. So here's a little introduction. So far we have only solved first order differential equations by using separation of variables. However, not all first order differential equations can be solved this way. There are many other methods you'd have to learn to become a supreme ruler of differential equations, but luckily you don't have to. And you can thank Leonhard Euler, and he lived from 1707 to 1783. He was a Swiss mathematician and physicist, and is best known in the math world for the discovery of the number e. In very simple terms, Euler's method allows us to find approximate solutions to a non-integrable differential equation by using tangent lines. So, Euler's method. So we're going to first look at it graphically. So if we have a slope field for the differential equation dy dx equals x plus 1 and have the particular solution through the point 0, -1. So here's our graph. The idea is to approximate the y value on the particular solution at an x value that is close to the initial condition. So what that means is we're going to start at initial condition. We're going to call that x naught, y naught, and define a new point, which is going to be x naught plus your change of x, comma y naught plus your change of y. Then we're going to connect the 2 points with a line. The process is then repeated, starting with the new point. The end result will be a graph made up with lots of small lines that are close to the actual graph. And we are approximating the curve with a series of slope field segments. So this is what this would look like. So in both pictures, the blue curve represents the actual solution. And then in this first one, the pink is the approximation. So notice how here's our initial condition. Then we have some other point that's a certain distance away. And we find that line and then connect the dots. And then we start from this point and so on. And you'll notice that the approximated curve is fairly similar to the actual curve. So what does it mean numerically? So let's look at the example given that y of 1 is equal to -2. So we have our initial condition, 1, -2. And dy dx is equal to 2x minus y. What is the approximation of y of 3 if the step size is 0.5? So the step size is representing your change of x. So you're going to first start by starting with the point x naught, y naught, so your starting condition. And this point will be on the graph as required. So here's my starting point. I am then going to use the differential equation to find the slope dy dx at that point. So using my dy dx equals 2x minus y to get the slope of the tangent line at that point, I'm going to plug in 1 for x and -2 for y to get a slope of 4. My third step is I'm now going to increase x by a small amount that I'm going to call the change of x, and increase y by a small amount, which is the change of y. But where the change of y equals the slope, dy dx, times the change of x. This defines my new point, x naught plus change of x, comma y naught plus change of y, that lies along the linearization. So the step size is what we call your change of x. So in this picture, you'll see here's your curve, right? And here's your tangent line. Here's my starting point, or my initial condition. And then to get to the next point, you're doing your change of x. And then to get your change of y, that is your slope times your change of x. So in this example, my change of x is 0.5. So therefore, my x sub 1, or the next point after my initial condition, is going to be my initial x, 1, plus my change of x, so 1.5. Now to get my next y value, I'm going to take my initial y value, -2, and I'm going to add the change of y. But to get the change of y, that is going to be my slope at the previous point, which was 4, times my change of x, which is 0.5. So then that means, after simplifying, my next y value is 0. So my next point is going to be 1.5, 0. So now using this new point, I'm going to return to step 2 and repeat this process until you get to what you want to approximate. And graphing each new point constructs the graph of an approximate solution to the differential equation. All right, so I'm going to continue this. So my in is my start. So my starting spot is 1, -2. My next point, so my first point, my sub 1 point, was I just found 1.5, 0. Now I need to find the second point, because I want to go all the way up so I can approximate y of 3, because that's what the original example wants me to find. So that means I have to do this at least 3 more times, because my step size is 0.5, so to go from 1 to 3, I'm going to have to do it a few times. So I'm still using my dy dx equals 2x minus y. So to find the slope for the next tangent line, I'm going to use the differential equation, but this time for x and y, I plug in my sub 1 point. So 1.5 for x and 0 for y. Simplify. This time I get a slope of 3. And I'm going to find y sub 2, which is going to be my previous y value, so in this case 0, plus the change of y, which is my dy dx, times the change of x. So my next y value is 1.5. So that means my next point is going to be 2, 1.5. Now I'm going to keep doing this, but this time when I evaluate the slope of the tangent line, I'm going to use 2, 1.5. So find the slope of the next tangent line, simplify. Find the next y using the previous y, and simplify. So my next point is 2.5, 2.75. Now I'm going to do it again one more time. So this time using the point 2.5, 2.75. Plug it in to get my slope of 2.25. Find the next y value by using the previous y value. So the next y value is 3.875. And notice that this gives me the y value when x is 3. So I have finished approximating. So what this means is that the approximate value of y of 3 is 3.875. And the actual value for the particular solution at x equals 3 is 3.7293. And I found that using my calculator. And if you want to look at a graph of what we just did, the blue curve is my particular solution. And then the pink one is the approximated. So the pink one represents each of the tangent lines going from this point to here and so on. And notice here when x equals 3, that's a very, very close. It's a very small error. All right, so let's do some more examples. All right, let's look at this differential equation. dy dx equals 5x squared minus 6 over y minus 2, where y cannot equal 2. And we're going to let y equals f of x be the particular solution to this differential equation with the initial condition f of -1 equals -4. And we're going to use Eulers method starting at x equals -1 with 2 step sizes of equal size to approximate f of 0. So show the work that leads to your answer. So since I want two steps of equal size, and since I'm starting at x equals -1, and I want to go to 0, that means that my change of x is going to just be 0.5. So I only have to do this twice, which is nice. All right, so I'm going to first find the slope at -1, -4. Plug in those x and y values. Simplify to get a slope of 6. Now find the y value, the next y value, using the previous y value plus the slope times the change of x, which is 0.5. Simplify to get a -1. Now you find the slope at the next point, -0.5, -1. Plug that into x and y into the differential equation to get a slope of 3.25. Find the next y value using the previous y value. Simplify to get 0.625. So this means that on the particular solution, when x equals 0, y equals approximately 0.625. All right, now why don't you go ahead and try this one on your own? All right, let's see how we did. All right, so in this example, we want to approximate f of 2 starting at x equals 0 with 4 step sizes of equal size. So that means I'm going to have to start at 0 in order to go to 2 with 4 steps. That means my change of x is going to be 0.5 again. So I'm going to be approximating the y values at the following 4 x values until I get to 2. So I'm going to start with the slope at 0, 2, which I get 1. Find the y value, which is 2.5. Then do it again at this new point, 0.5, 2.5, and I get a slope of 2.149. Find the next y value, which is 3.574. Find the next slope using this new point, and I get a slope of 4.293. Find the next y value, gives me 5.721. And then my last time, find the slope, which is 8.202, and find the final y value, 9.822. So this tells me that on the particular solution to this differential equation, my approximated y value when x equals 2 is 9.822. All right, now let's see how we did on number 3. So in this one, we want to approximate c, so some y value, when x equals 4, using Eulers Method with 3 steps of equal length. So I'm starting at 1 and I'm going to 4. And since I only want 3 steps, in this case, my change of x is just 1, which is nice. All right, so I'm going to go ahead and find the slope at the initial condition, 1, 3. Now I find my next y value, which ends up to be 7. Find the next slope at 2, 7. Find the next y value, which ends up to be 11.5. Next slope, which is 4.833. And then my final y value, 16.333. So for this one, my y value when x equals 4 is approximately 16.33. Well, I hope you enjoyed learning about Eulers' method, and I will see you in class tomorrow. Have a good night.